Pressure is the force applied perpendicular to the surface of an object per unit area over which that force is distributed. Gauge pressure is the pressure relative to the local atmospheric or ambient pressure. Various units are used to express pressure. Some of these derive from a unit of force divided by a unit of area. The SI unit of pressure, the Pascal, for example, is 1 Newton per square meter. Similarly, the pound force per square inch is the traditional unit of pressure in the imperial and US customary systems. Pressure may also be expressed in terms of standard atmospheric pressure. The atmosphere is equal to this pressure and the torr is defined as 1/760th of this. Manometric units such as the centimeter of water, millimeter of mercury and inch of mercury are used to express pressures in terms of the height of column of a particular fluid in a manometer. Definition: pressure is the amount of force acting per unit area. The symbol for pressure is P or P. The IUPAC recommendation for pressure is a lowercase p. However, uppercase P is widely used. The usage of P versus P depends on the field in which one is working, on the nearby presence of other symbols for quantities such as power and momentum, and on writing style. Formula: mathematically, where is the pressure, is the normal force, is the area of the surface on contact. Pressure is a scalar quantity. It relates the vector surface element with the normal force acting on it. The pressure is the scalar proportionality constant that relates the two normal vectors. The minus sign comes from the fact that the force is considered towards the surface element, while the normal vector points outward. The equation has meaning in that, for any surface S in contact with the fluid, the total force exerted by the fluid on that surface is the surface integral over S of the right-hand side of the above equation. It is incorrect to say, the pressure is directed in such or such direction. The pressure, as a scalar, has no direction. The force given by the previous relationship to the quantity has a direction, but the pressure does not. If we change the orientation of the surface element, the direction of the normal force changes accordingly, but the pressure remains the same. Pressure is transmitted to solid boundaries or across arbitrary sections of fluid normal to these boundaries or sections at every point. It is a fundamental parameter in thermodynamics, and it is conjugate to volume. Units: the SI unit for pressure is the Pascal, equal to 1 Newton per square meter. This name for the unit was added in 1971. Before that, pressure in SI was expressed simply in newtons per square meter. Other units of pressure, such as pounds per square inch and bar, are also in common use. The Cgs unit of pressure is the Berry, equal to 1 dYNCm-2 or 0.1 pascals. Pressure is sometimes expressed in grams force or kilograms force per square centimeter and the like without properly identifying the force units, but using the names kilogram, gram, kilogram force, or gram force as units of force is expressly forbidden in SI. The technical atmosphere is 1 kilogram force per square centimeter. Since a system under pressure has potential to perform work on its surroundings, pressure is a measure of potential energy stored per unit volume. It is therefore related to energy density and may be measured in units such as joules per cubic meter. Some meteorologists prefer the hectopascal for atmospheric air pressure, which is equivalent to the older unit millibar. Similar pressures are given in kilopascals in most other fields, where the hecto prefix is rarely used. The inch of mercury is still used in the United States. The standard atmosphere is an established constant. It is approximately equal to typical air pressure at Earth mean sea level and is defined as 70051013250000101,325 pascals. Because pressure is commonly measured by its ability to displace a column of liquid in a manometer, pressures are often expressed as a depth of a particular fluid. The most common choices are mercury and water. Water is non-toxic and readily available, while mercury's high density allows a shorter column to be used to measure a given pressure. The pressure exerted by a column of liquid of height h and density ρ is given by the hydrostatic pressure equation P equals ρgh, where g is the gravitational acceleration. Fluid density and local gravity can vary from one reading to be another depending on local factors, so the height of a fluid column does not define pressure precisely. When millimeters of mercury or inches of mercury are quoted today, these units are not based on a physical column of mercury, rather, they have been given precise definitions that can be expressed in terms of SI units. 1 millimeter of mercury is approximately equal to 1 torr. The water-based units still depend on the density of water, a measured, rather than defined, quantity. These manometric units are still encountered in many fields. Blood pressure is measured in millimeters of mercury in most of the world, and lung pressures in centimeters of water are still common. Underwater divers use the meter seawater and foot seawater units of pressure, and these are the standard units for pressure gauges used to measure pressure exposure in diving chambers and personal decompression computers. A MSW is defined as 0.1 bars, and is not the same as a linear meter of depth, and 33.066 FSW equals 1 atmosphere. Note that the pressure conversion from MSW to FSW is different from the length conversion. 10 MSW equals 32.6336 FSW, while 10 meters equals 32.8083 feet. Gauge pressure is often given in units with G appended, e.g. kPa(g), bar(g), or pSig, and units for measurements of absolute pressure are sometimes given a suffix of a to avoid confusion. For example, kPa, pSia. However, the U.S. National Institute of Standards and Technology recommends that, to avoid confusion, any modifiers be instead applied to the quantity being measured rather than the unit of measure. For example, Pg equals 100 psi, rather than P equals 100 pSig. Differential pressure is expressed in units with D appended. This type of measurement is useful when considering sealing performance or whether a valve will open or close. Presently or formerly popular pressure units include the following: atmosphere, manometric units, centimeter, inch, and millimeter of mercury. Height of equivalent column of water, including millimeter, centimeter, meter, inch, and foot of water. Imperial and customary units: kip, short ton force, long ton force, pound force, ounce force, and pound per square inch. Short ton force and long ton force per square inch. FSW used in underwater diving, particularly in connection with diving pressure exposure and decompression. Non-SI metric units: bar, decibar, millibar. MSW used in underwater diving, particularly in connection with diving pressure exposure and decompression. Kilogram force, or kilopond, per square centimeter. Gram force and ton force per square centimeter. Berry, kilogram force and ton force per square meter. Thien per square meter. Examples: as an example of varying pressures, a finger can be pressed against a wall without making any lasting impression. However, the same finger pushing a thumbtack can easily damage the wall. Although the force applied to the surface is the same, the thumbtack applies more pressure because the point concentrates that force into a smaller area. Pressure is transmitted to solid boundaries or across arbitrary sections of fluid normal to these boundaries or sections at every point. Unlike stress, pressure is defined as a scalar quantity. The negative gradient of pressure is called the force density. Another example is of a common knife. If we try to cut a fruit with the flat side, it obviously will not cut. But if we take the thin side, it will cut smoothly. The reason is that the flat side has a greater surface area and so it does not cut the fruit. When we take the thin side, the surface area is reduced and so it cuts the fruit easily and quickly. This is one example of a practical application of pressure. For gases, pressure is sometimes measured not as an absolute pressure, but relative to atmospheric pressure. Such measurements are called gauge pressure. An example of this is the air pressure in an automobile tire, which might be said to be 220 kilopascals, but is actually 220 kilopascals above atmospheric pressure. Since atmospheric pressure at sea level is about 100 kilopascals, the absolute pressure in the tire is therefore about 320 kilopascals. In technical work, this is written, a gauge pressure of 220 kilopascals. Where space is limited, such as on pressure gauges, nameplates, graph labels, and table headings, the use of a modifier in parentheses, such as kPa or kPa, is permitted. In non-SI technical work, a gauge pressure of 32 psi is sometimes written as 32 psig, and an absolute pressure as 32 psia. Though the other methods explained above that avoid attaching characters to the unit of pressure are preferred. Gauge pressure is the relevant measure of pressure wherever one is interested in the stress on storage vessels and the plumbing components of fluidics systems. However, whenever equation of state properties, such as densities or changes in densities, must be calculated, pressures must be expressed in terms of their absolute values. For instance, if the atmospheric pressure is 100 kilopascals, a gas at 200 kilopascals is 50% denser than the same gas at 100 kilopascals. Focusing on gauge values, one might erroneously conclude the first sample had twice the density of the second one. Scalar nature in a static gas. The gas as a whole does not appear to move. The individual molecules of the gas, however, are in constant random motion. Because we are dealing with an extremely large number of molecules and because the motion of the individual molecules is random in every direction, we do not detect any motion. If we enclose the gas within a container, we detect a pressure in the gas from the molecules colliding with the walls of our container. We can put the walls of our container anywhere inside the gas, and the force per unit area is the same. We can shrink the size of our container down to a very small point, and the pressure will still have a single value at that point. Therefore, pressure is a scalar quantity, not a vector quantity. It has magnitude but no direction sense associated with it. Pressure acts in all directions at a point inside a gas. At the surface of a gas, the pressure force acts perpendicular to the surface. A closely related quantity is the stress tensor sigma, which relates the vector force to the vector area. Via this tensor may be expressed as the sum of the viscous stress tensor minus the hydrostatic pressure. The negative of the stress tensor is sometimes called the pressure tensor, but in the following, the term pressure will refer only to the scalar pressure. According to the theory of general relativity, pressure increases the strength of a gravitational field and so adds to the mass-energy cause of gravity. This effect is unnoticeable at everyday pressures but is significant in neutron stars, although it has not been experimentally tested.